This kind of an old presentation from 2009. And at that moment, I was just explaining what were the problems that were still unsolved in the kinematic synthesis. The fact is, most of them are still unsolved, except the ones we have been working on, because nobody else in the world works on that. That's not right, but almost. All right, so let me just show you, and this is all that you know about. So this kinematic synthesis determine the mechanical constraints in order to perform the motion. Here you have the set of task positions defined in space. So this is the task we want to accomplish in this case. This is a possible robot able to do that. Can you see that more or less well? Yes. And basically, I mean, in this one we were trying to illustrate, how many different solutions you have. When you have serial chains, you have a few, but when you start assembling them and creating parallel robots, then these are all the possible combinations of basic joints. So you have, hundreds of thousands of possible structures you can use to perform these motions. Just starting with these simple revolute, prismatic, cylindrical, spherical joints. Okay. So it's just the number of possible structures you can use, topologies. Those are the joints: revolute, prismatic, cylindrical, universal, and spherical. This is, the finite set of positions task. This would be a continuous trajectory, and then you could select a robot like this one has 1, 2, 3, 4, 5 axes. This is a 5R serial robot, that you could design to do the task. So these are different ways of stating these equations that people have used in the past. These are the basic methods. Loop, these are the loop equations that we were talking about. And then this is the robot kinematics equations, which are the ones we are going to use. And so, the challenges that I was explaining, one is to be able to state the design equations. That's the first one. So we can create very simple equations for a few particular cases, but we cannot generalize them to any robot. But if we do the method that we are going to use, then you end up with many equations, big systems of equations with extra variables. So for instance, I was telling you the simplest robot is the revolute chain, and you can state 10 equations to solve for it. If you go to the 5R, 5 revolute joints, we can use the kinematics equations. We get 130 equations, okay, just to solve for this simple thingy here. We should be able to state a system with only 30 equations, because those are the variables. It's 30 variables. In fact, it's 5.410. It's a little bit less than that, but. And then the other challenge is to solve this system. So once you have this big system of equations, what do you do with it? So for instance, this one, it's 10 equations quadratic, so in principle the total degree, you can bound it at 1024 solutions, but it only has 6 solutions in reality, so the equations simplify a lot, and we cannot go with this. That's a waste of computer power and a lot of waiting time and so on. For instance, for this one, which is a revolute, a prismatic, and a revolute joint, if you calculate the total degree of the equations, as more simplified equations we can do, 32,700 solutions, but it only has 12 solutions. So we have this problem that in the small cases is what we call the complexity in the middle. So you have this very simple system, you state a system of equations that is very complicated, your solutions are also simple again, but how do you go over this mountain? How do you make a tunnel, that you can go from simple to simple? That's happens many times. But it's not always complexity in the middle. These systems, when you start adding more joints, they become really complex. For instance, these are revolute, prismatic, and then a spherical wrist at the joint at the wrist. It's a 5 degree of freedom robot. Well, okay, the initial total degree is 200,000 and something, so it's big, but some people have been able to find 1,000 solutions, so 1,000 different RPS chains that can go through, however many positions you define. So these are the ones that I was telling you that have been solved already, and they are really small. And okay, there it is. And then some other special cases, when you have a spherical joint at the wrist, then things simplify because you can look at just at the point. You don't need to worry about the orientation. The orientation will be whatever you need to have, and then it can simplify. But we are talking about, for instance, for the RPS, 36 real solutions. Some other of these cases can have 200,000 roots. So. All right, so this is just the theory that we have seen. So create the relative kinematics equations, counting how many positions you can define at most, create and solve the equations. All right, so just going to go fast through this. And this is just an explanation of the kinematic equations. Clifford algebras, you guys know all this perfectly. So this will be the expression of a cylindrical joint, where you can rotate an angle theta and slide an amount d. And this would be the expression of the motion about this joint in dual quaternions. The same thing, if we were going to use a matrix, this is the expression of a rotation about a known axis if you express it in matrix form. So it kind of becomes big. Matrices sometimes are not the simplest. So here we have our kinematics equations. Here what we do is this is our kinematics equations for M joints, and we equate that to the positions we want to reach. And that's how we create the equations. This is the counting that we did the other day. So this is the 5C serial chain, and we took this as the most general case because if you have a cylindrical joint, if you want to convert that in a revolute joint, then just state that the displacement is equal to 0. If you want to transform this in a prismatic joint, just say that the rotation is 0. So you can create any RP combinations using just the cylindrical joint, that's the generic joint. So this will be the forward kinematics equations, and this is the exponential notation. This is basically the exponential of the axis times the angle over 2 is a rotation about that axis. And we haven't done this theory, but so let's take it as just a notation. Okay. And then you can count the terms, and I was implementing a solver here, so I did a lot of counting. But
what is the software which you are using?
This is called Synthetica, and it's a software that was done at a lab, but hasn't been maintained for many versions. So I think the last one is from 2009 or something like that. I can give you the link to where it is, but I'm not sure it will work in the new computers. You guys can try and see if it works. But it's nice because I implemented a general synthesizer there, so you define the chain you want just with the letters. You just put your positions there, you can enter your coordinates, and they will appear there on the screen, and it will give you a robot. So it just gives one solution at a time, and then it just draws the robot. Okay, it's a nice software. It's a nice little piece of software. You can also draw your robots and things like that. And then I talk about the open problems in kinematic synthesis, and most of them are still working on them. And the first one is the one that now Ali is taking care of. We are trying to, so it's really just a 3R robot. How many different 3R robots can we make to go through 5 positions? It's just a mathematical simple question, and it's not solved yet. It has been done using interval analysis, and of course that depends on what positions you use. So the only thing they could say is, okay, for this interval that we have taken and for these positions we got 13 solutions. I know if you do a lot of runs, then I got this number, 10, 12 or 18, depending on the set of positions that you get real solutions, and then complex solutions, maybe many more, we don't know. So this is still open. We are trying to solve this using Grosvenor bases. And then what do we do with the rest of them? Is it really a complexity in the middle problem, or is it really complex by itself and we will never be able to simplify? So do we give up in finding a simpler way of creating these equations and just go for a numerical solver, or do we keep trying? And this is one of my tests, and this is for a 4R. So 4 revolute joins, 1, 2, 3, 4. And then I just run it many times, with the same positions. And I keep finding more and more solutions. If I run it 10,000 times, I get 6,000. If I run it 20,000 times, I get 14,000 solutions. And they are repeated, so that means that there are no infinite number of solutions, but the number of solutions are very big. This over here, this is the locus of all orientation of the axis. So each color means one of the axes. So the yellow may be the first one, the purple may be the second, and so on. So basically it's all over. It's all over. There are solutions everywhere, and this is the location of the axis. So they concentrate around the task more or less, but there are.
Is it for the same task or different tasks?
This is for the same task. So these are all solutions. So these are the 14,000 solutions that can go through this task. It's different robots. So one is this, another one will have longer here, shorter there, it will be located somewhere else. 14,000 of them, and if I run it 50,000 times, then I'll get, I don't know. You see, the number of different solutions keeps decreasing. So I'm sure there is a probability formula that will tell you, given these numbers, what's the expected number of solutions, right? Because there is some.
Last one is the last one.
So this is 10,000, but we need to go to 100%. I mean, percentage of different solutions out of the number, going, I guess. Anyway, it's just to see that the problem is big and it's unsolved, but it is big itself. I mean, it will have many solutions, so we cannot expect to find a univariate polynomial, something very simple for these cases, but maybe for the small ones. So that was one open problem. We are still working on that. Then we needed a good solver, and we worked on that, and we have R-tricks now that works very well. Okay, so it can solve, for instance, the 5R, the 130 equations in just seconds. So that we did, so it's more or less okay. The only problem is it only gives one solution every time you run it. And that's another thing we are trying to do, is to find a solver that will allow us to find all the solutions. That's what we are doing with Peter at a very basic level, our undergrad. We are trying to implement this in a solver that is called Quick, which is an interval analysis solver, but with some tricks we may be able to find all the solutions. Then another thing is the synthesis of parallel robots. I mean, serial robots are complicated, but parallel robots are much more complicated. And that's part of what Jim Esker has been working on, which is define the whole workspace. Because if you just define positions with parallel robots, you cannot ensure that you will go from one to the next. You may have constraints that will not allow you to do that. Anyway. And then this is just possible things. And then this we started doing, but in fact we didn't continue, which is a very interesting problem. But you can handle just as many problems. This is, you have an image of a motion. Can you derive from that image of the motion what is the thing performing the motion? Okay, and the difference between the 3D motion that we define with position and orientation and an image is that you have the projection there. So your matrix, instead of being a matrix with a orthogonal upper 3x3 and then a vector there, has many more variables in there, because things in the image, things can be deformed, right? So you have extra parameters. So it's a very interesting problem from a math point of view, but we never continued that. We did some work with the cameras, but it was hard from us from the computer science point of view. For instance, we needed to identify some particular points on the thing you are following, and get the very precise 3D pose of those things that you are tracking. So we kind of gave up and went to the Vicon system, which is already there. Right? All right, so this is all our work on the cameras. We can leave it. Oh, that's, I should make this one run. So this was our synthesis to recover the motion of a person.
He's dancing?
It's moving the arms crazily so that we have. You know, one thing that we notice is it's you see, sometimes this is our recovery, and then sometimes you see that the solution is not good. But one thing we notice is that you need to have a lot of motion in order to do the synthesis well. So if you just do one motion, you don't have enough. You need to do all possible motions. But we humans, that's something we notice, we are always moving, even if we don't move. There's always a small motion in our joints, and that makes it easier to do. Anyway, yeah, that's nice, huh? Yes. All right, so this is the projective environment. So this is what I was telling you about. This is just the rigid motion, rotation matrix, upper 3x3 is orthogonal, and then you have this vector. That doesn't change the shape. When you go to a projective environment, you don't have this 0, 0, 0, 1 and this part being orthogonal, because depending on your point of view, you will see these as deformed, and you have to take that into account when you do your synthesis. Maybe one day we will retake it, or maybe somebody else will solve it, but right now it is not. The other thing we were going to apply this synthesis to is mechanisms that we call lattice mechanisms, which are just like networks of mechanisms. And those, of course, if you take every individual mechanism and try to do the computation for everything, becomes just incredibly costly. So the idea was to look at symmetries from cell to cell, and that's something also that is stopped right now, but maybe one day we will go back to that. I'm not sure if I have any. This is something we did. Oh, is that it? Oh, there it is. So this is you cannot see here, but every little element is one square, similar to these ones. And this was done for a project for DARPA. They wanted a airplane wing that will change shape. Okay, so this is the wing changing the shape, and didn't get the contract, the people we were working with. So anyway, we did that. These are the same ones, and that's it. There are many interesting problems to work on kinematic synthesis, so I guess that's the conclusion. And one thing that I didn't mention here, because at that point we weren't working on it, was the synthesis of the hands, and that's something that appeared to us. Maybe I'll show you that. So this happened when we were trying to, just recover the skeleton of the hand. So we were trying to use synthesis with images to try to recover the internal skeleton of the hand, and then we put that in the solver that we had just implemented, the R-tricks, and this is what we got. So the green lines, so these gray lines are corresponding to the human hand, kind of, and the green lines is the hand that we found. And then we looked at it, it's like, wow, maybe we can design hands that can move as the human hand, but be kind of crazy. And that's how we started using the synthesis for the design of hands, which is what we are doing now. Okay. It will be nice to see this thing moving, completely crazy thing. Anyway, so this is what we need to be doing. What we had done, let me just say about the kinematic synthesis. We had created a task, right? As a set of positions. P is 1i, I equal 2 to m, and then we had the forward kinematics equations, which were S1 of theta 1i, Sn of theta n I, so that means going to position I. Just little touch. Theta and I. And then we had created the design equation, but by just equating those. So we counted M max in order to get exact synthesis, right? For exact synthesis, and then we just equated those, right? S1 theta 1 Sn theta n I equal to P1 I equal to up to M, and that's how we got our system of these are dual quaternions, so it will be 8 equations each. We know 6 of them are independent, 2 of them are just constrained by the conditions of the dual quaternion, but in principle if we just equate this we will get 8m minus 1 equations. And in these equations we have to locate the dimensions of the system, which are given by the Brucker coordinates of the axis, right? Let me just find S1 Sn Brucker coordinates, but then we also have the angles, and the angles are not really fundamental parameters of the design, so we could, if possible, we would like to get rid of them. Okay, we have theta 1 to theta n, but you know, at each position, so I equal to 2m joint variables. So if we could simplify the equations, eliminate the joint variables from them, the equations will become simpler, and that would be good for us. We don't really need this right now. We'll need them later for doing the inverse kinematics, but that's not important. So the design equations are parameterized by those equations are parameterized by the theta ij's. Those are parameters. If you give values to those, you will move, you know, the robot, right? We want to eliminate. To eliminate them, if possible, because so far it has been a hard task. But this is one of the things that, you know, using Grobner bases, we may be able to eliminate out of all this list of variables. Imagine if you have, you know, 3 jointed robot with 5 positions. Here you have 3 times 5, 15 extra variables. You may want to eliminate those and keep just this as your variables in your equations. This is, we can call that implicitization. Okay. It's not very easy to eliminate those, but let me show you some structure that these equations have, and that may help. So the dual quaternion design equations They are nice. They have some structure. Have the following structure. So let's take that previous one. So we have S1 theta 1. Let's just put it in generic for a position, okay? Sn of theta n, so that we don't have to carry the I index equal to P, okay, just for one position. So you can actually, when you do this product, using the Clifford product, you will have all the cosine and sine multiplying each other. You can actually write this, you can organize them in the following way. So here you have, this, I'm not sure if whether, let me just put it 8 by 8. So I'll just take the 8 components of the dual quaternion and I'll just put them in line, okay? So we'll have 0, 0, 0, 0, 0, 0, 0, 1 will be the first column, and then we'll have S1, that means the real part and the dual part, one after the other. S2, Sn, these are all columns. And then you have S1, S2. This is the geometric product of the axes only. I'll show you that. S1, Sn, S2, S3, S1 is so S2, S3, Sn minus 1, Sn. So all possible products 2 by 2, and then the same thing 3 by 3, 4 by 4, up to the last one will be S1, S2, Sn. So you have this big matrix. And then you multiply this times all the combinations of angles, okay? And you have as many columns of this. So here you will have all the cosines. Cosine 1, cosine n. When an axis appears, then you have a sine instead of a cosine. So this will be sine 1, cosine 2, cosine n. Sine 1, cosine 2, cosine n. The third one will be cosine 1, sine 2, cosine 3, cosine n, and so on. And the last one, where all the axes appear, that's all sine. Sine 1, sine 2, sine n. And that is equal to P, okay? So it has a nice way of separating the joint variables from the structural variables, which is very easy to do systematically. So we are done, right? So we can just solve for this. We can do like an inverse kinematics, and then, but this matrix you cannot invert it always because it's not square. It's square only in a few cases for very low degrees of freedom, so it's not so easy. One possible idea would be find the values for this, plug them back in, and then you will have all structural variables, but that gives very, very complicated equations. But anyway, you can always do this kind of structure, and that gives some hope that we can eliminate this. In fact, there are ways of using resultants, kind of simplify this over here. So bottom line is we cannot eliminate this simply. We wish, but let me show you what these are before, so S1, the S1 that we put here is not the Plucker coordinates of this is a 8-dimensional entity. So what you have is the direction, and then a 0 as the number, plus epsilon, the moment, and a 0, okay? So this is what it's called a pure dual quaternion, when you have the zeros in the number, okay, in the scalar. Okay. Oh, and I see that the notation is should. These are big S. These are not small s's. Okay. These are capital S. These are little s. Should have done them bigger. Let me just make them bigger so they don't get confused. S1, Sn, all in one. These one are big too. These are small. So this C1, this little C1 means cosine theta 1 over 2. Little S1 means sine theta 1 over 2, and so on. Okay. And this big S, those are the Brucker coordinates of the axis. Alright, so what I wanted to do is just to do some cases and for you to see the design equations that we get. So maybe let's just take Mathematica and do one example. Let me just do that. Mathematica. Now the equations you get, Mathematica can solve maybe the first simple example or the first two simple examples. After that, you need to create your equation and send them to the solver to be solved. Okay. So hopefully we will be able to make our tricks work for us because it's really fast. And the only thing you need to create is to create a Lua file. So we may have Ali give us a Lua class in this so that we all know how to create that Lua file for our system. It's really easy. You just define your joints, define your task. It creates your forward kinematics equations automatically. So it's really nice. Okay, so let's go to mathematics. So if we let's do the first example. Let me go back to we'll do the simplest case, okay? If you can find your files, you can download them and work with your computer. Please do so if you want. So first example. What should we do? RR? Just a double, two revolute joint robot. RR robot. Okay. So we use our formula. How was that? So we have R equal to 2 revolute joints. So the maximum number of position was, I forgot. Okay, let me just derive the formula again because we have 6 equations times the number of positions minus 1 equal to 4 and 4, 8 plus 2 joint variables. So, okay, what is this? Let's see. 6 minus 2 is 4m equal to 8 plus 6 minus 2, 12? No, 12. Okay, so m equals 3. Alright. Alright, so we can define 3 positions. So let's start by doing that, creating the forward kinematics equations, equating those to those positions, and then solve and get a robot. See if we can do that. And we need Mathematica for that. Okay. Yeah, take the suggestions. Okay, so we need to define just 3 positions. So let's just put here 3. Okay. 3 positions. Okay, so each of these lines corresponds to a displacement from the origin to a given position, and we can plot them so that we can see what positions we chose. And this was all. Oh, and now we have to. You know what? Let me just create a variable here for the number of positions. N equals 3. Okay, so now I can go from 1 to n, and I don't have to keep doing this over and over because here I have another 10. Bad programming, you always pay for it. Okay, so this was the line, this was the axis. N. Okay. And that's all right. why is it only one? Okay. Black line, line. Oh, okay. I don't know what was this. It was just one, right? Okay, so we should see the 3 positions here. Okay. So the black one is the origin, and these are the 3 positions we have defined. So our system has to go through this position with this orientation that is given, right? All right. So now we create the relative positions, which are the ones we will use, and if we had 3, then obviously we'll have n-1, and these are the relative positions, even though, you know, that doesn't give much information. So with this we define the positions. Now let's do the forward kinematics equations. So this one, instead of positions, we are going to call it kinematic synthesis example. Our finite positions for RR robot. Okay. Save as desktop. We're in the desktop. Let's call it forward kinematics equation synthesis. Okay. So those were the positions, those were the relative positions, and now another section 3 will be create forward kinematics equations for the RR robot. And we know how to do that because we create a quaternion. Okay, let me just copy this. We create a dual quaternion, but with an axis which is unknown. So let's just define our axis. Let's say S1 will be equal to S1x, S1y, S1z. So this is our unknown direction plus epsilon S1x0. This is the moment. S1z0. So this is the first axis, and then we have 2 axes, so we don't need to. I'm just going to copy and create the second one. This is what we need to solve for, and this is the joint axis at the first position, at the reference configuration. 2x0, 2y0, 2z0. Okay. Now the dual vector will be S1, but I believe that you need to put it as 2. I believe you need to use the sep q, q2 S1. Let me see. Yeah. So we need to, for this function, we need to put it in the form of 2 vectors instead of this. So it's the dual vector, and the angle will be just unknown also, so we are going to call it theta 1 for the first axis, and then the slide along the joint is 0 because it's a revolute joint. Okay, so this creates our first quaternion, and let's call it, this is the rotation about axis 1, QS1. Okay, and everything is unknown because we need to find those. And then we do the same thing for the second one. We are just writing the forward kinematics equations here. QS2, we do the same thing for S2 and theta 2. And we just multiply them, and that gives the relative forward kinematics equations. So, okay, that was not a good idea. Delete. Backspace, delete. Okay, there we go. Okay, so I want to put some text. Okay, here. Forward kinematics equations for relative displacements from the first position we have defined. Okay. So we just multiply those two, right? Quad mult QS1, QS2. And this is the forward kinematics equation. So forward kinematics equations equal to that. Maybe we can simplify. Okay, let's just collect this by epsilon, and then simplify each term that you collect. Okay, it wasn't much better, but these are the forward kinematics equations. They are not huge. They are just this big. Okay? So the idea is, if you know your axis, you give values to your joints, you get the position of your end effector as a motion from the first configuration to the second. What you get here is a motion, okay? Alright, so we equate this motion to the relative positions which we have defined here. These are the relative positions from the first one. Is the second times the one inverse, the third times the first inverse. Okay, so poses rel. So let's call these design equations. Will be equal to FKA minus poses rel of I. So we have two sets, so we are just going to make a table with two values. Table is like an array. I going from 1 to 2. That's not great, but let's see if that works. Alright. So here we have the values we have equated to. Okay. It's already putting everything in. This has the epsilons and all, and in order to solve for these equations, let's get rid of the epsilons. So let's do a sep q for each of them. Sep q, which separates the components and gets rid of the epsilon. Okay. All right. So now we have our system of equations. This is our system of equations. This is the desired position equated to the component of the dual of the forward kinematics and so on. And this is the first set. So this is the set for the first position, and this one is the set for the second position. Okay? So let's see how many equations we have. Let's just flatten them, which means put everything in a single vector. So let me just call this F2 equal to flatten design equations. And now let's calculate the dimension, and that's calculated with the command length of this F2. We have 16 equations. How many unknowns? Oh, we did something wrong, sorry. We have to go back. The thetas are not the same, so we need to change the name of thetas when we do this, okay? One is theta 1, 1, and the other is theta 1 for position 2, okay? So let's see. Let's do it here. FKE okay, let me see. How can I do it so that I can do it in one step? Let me just put it here. Theta 1i and theta 2i. Okay, bad programming, but let me just create this. Theta 1, 1, theta 2, 1. That will be the first set, and then theta 2, 1, theta 1, 2, theta. There is ways to assign the names, but you have to use lists of strings and things like that, which are more complicated to program. So the first set will be the variables for reaching the first position. The second one will be the variable for reaching the second position. So now we can just evaluate to that set. This such that theta 1 goes to thetas of I, 1 and theta 2. Okay. If something is not clear in Mathematica, let me know. I, 2. Okay. Alright, so now we are substituting that. Hopefully that will work. Now we have many more thetas, right? So this will be theta 2 for position 1, theta 1 for position 1. Then you go to the second position, theta 2 for position 2, theta 1 for position 2. Have different values of the joint variables. So 16 design equations, and how many variables? So we have, okay, let me just, I'm going to just write that. Joint or variables. So we have 16 design equations, but remember those are 8 equations and only 6 of those are independent. So we have 6 and 6, 12 independent design equations. And we have, for each the Brucker coordinates of each line is 6, so we have 6 times 6, 12 joint, what we call structural variables, out of which are 8 are independent. Plus angles, we have 2 times 2, 4 angles, right? 4 joint variables.
Sorry, the first part, 6 times 6.
Where are we?
For joint.
Oh, for joints, we have two relative positions and 2 angles, right? So theta 1 and theta 2 for the first position, theta 1 and theta 2 for the second position. So that's 4 joint variables.
For links.
For the joint axis, we have 6 for the first axis, 6 for the second axis. Those never change because you move from the reference configuration to the second to the third. Okay, so that's 12, but only 4 of them are independent because the Brucker coordinates you have to constrain, right? One, the direction is unit. Second, the direction times the moment equal to 0. So at the end we end up with either 12, 8 times 4, 12, or 12 plus 4, 16. In this case it coincides, but it doesn't happen very often, okay? So the right thing to do would be to solve the independent ones. You can just get rid of 2 of them, any of them, and solve for the other ones. And then you have to substitute the joint variables, obviously, you know. Anyway, so we can solve for this, and I'm not sure we want to do that. You see, these are kind of complicated equations. Do you think that Mathematica will be able to solve this system of 16 equations in 16 unknowns? Should we try? It's surprisingly not very powerful, okay? But let's try. Let me save it first, because it may be that it will just say, hey, I can't. Okay, so let's say solve. All right? And how are they called? This design equation 2. In Mathematica, you have to equate the equations to 0. 1, 2, 3, 4, 5, 6, and 8, 9, 10. There is a way to do this better too, but anyway. So this is the equations we are solved, 16 equations, and now let's put the 16 unknowns. So that means S1x, S1y, S1c, S1x0, S1y0. I'm putting them like this so that you see them. Of course, there is S2x, S2y, S2x0, S2y0, S2z0. These are the structural variables, and now the angles. We had theta 1, 1, theta 2 for position 1, theta 1 for position 2, and theta 2 for position 2. All right. Now we can go have a coffee and then come back, okay? Because oh, it didn't like it. Say that again.
The first and
Oh, this is not right. That's why it's not like y1, right?
And yes.
1x0, 2x, 2z, S2. Oh, S1c, S2, 1. I think they are right now, right? Okay, let's try again. Okay, didn't like it. Okay, they say no, there is no solution. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. So there are 16, right? 16 equal.
There's Z1.
Oh, thanks guys. XC1 S. Oh, and these ones are also wrong, right? No. It's 2x. This is right. This S1x. That's why it wasn't solving. It's like, what are you trying to solve for? You don't even have those variables there. S1y, S1z. Okay, now. Right, let's try again. Didn't like it either. Anyway, yeah, we were just saying goodbye. So 16 equations in 16 unknowns. Doesn't want to solve them for some reason. Oh, hold on, we don't have, oh, I know why. Where are our design equations? Oh, I never execute the other one, sorry. So this one is this one, but I never execute the flatten, that's why. Okay, now it will. It didn't have the variables properly written. No, I didn't like it either. All right, well. Didn't like it. So Mathematica is pretty picky on the solve command. You have to have the same number of equations as unknowns. So another way you can do it is just select the independent equations and then add the constraints. Okay. So this doesn't work. Let's just write it down. Take the independent equations. Okay. And then we need to add some more equations. So the design equations 3. We'll try as once more and then will be equal to, we are going to take the first, these have the epsilon, right? So we will take the first 3 of each. Okay. Flatten. Okay. Table design equations 1, 2, 3. I, 1, 2, 3. So we'll take the first 3 components. We will leave the scalar out. Let me see. All right. So we should have 1, 2, 3, 4, 5, 6. This is 1, but where is the other one? This egg. Let me just look at this egg to make sure that we don't have. Oh, we already separated the equations here. Should. Okay, so that's a little bit more complicated. All right. Let me just put the sep q somewhere else. So let's have the epsilon. Let's put the sep q here. That should give us the same answer. And now we can use this one. And now we have to do the sep q in this one. Here. Anyway, little details. Okay, so we should have now 12 equations. 1, 2, 3, 4, 5, 6, 1. And we can look at the length, right? Equation 3. 12, okay. All right, so now we need to create our final set of equations. 4, okay, this will be. And let's see if it likes this one better. design equation 3, and then we will impose just our conditions for the Plucker coordinates. So that means S1, 1. Let me look at S1, how we define that. Okay, so sep Q2, S1. S1, the 1. Let me just do it manually, things clearer. So this one dot S1. So what I'm saying here is that the first vector is equal to 1, and I put too many parentheses. Let me just copy that. So these are the Plucker constraints for the axis. 2, 3, 4. The second one is S2. The second Plucker coordinates are also equal to 1, and then S1 times S1 0 is equal to 0, and S2 times S2 0 is equal to 0. Okay, let's see if now it works. Okay, so now we have all the equations, and here at the bottom, if you see these are just the first vector. The direction of S1 is equal to 1, direction of S2 is equal to 1, the moment times the direction is 0, the moment times 0. So this is again a set of 16 equations in 16 unknowns, right? So we can try again, let me just, the same thing but with the number 4. I know, and you will see that you will you will get tired of Mathematica trying to solve equations very quickly. Okay, we have 16 equations again, and we have 16 unknowns, right? Did you like it? I don't know. But what we will do is we will just write our equations and send it to our numerical solver.